All right. Hi, everyone. I'm Adithya, and today I'll be talking to you about our work on the problem of predictable verification and our solution for achieving it using a paradigm we call intrinsic definitions. This is joint work with Cody, Rivera, and my advisor, Madhusudan, and we're a team that's based out of UIUC. I will be moving to Madison soon. So I first want to talk to you about the primary frustration that we attempt to solve in this paper, right? So here's the picture of what you think verification should look like in practice. You have this verification engineer interacting with the tool. They give the tool their program and some annotations, and you expect the verification engine will say, yes, it's verified, or no, incorrect, meaning one of your VCs are invalid. So either the program or the annotation, something's wrong. But turns out this is not what it looks like in practice. There's a secret third option. Your verifier can just say, I don't know. And when it says, I don't know, the engineer is just stuck, right? They can move neither here nor there. They don't know whether it's actually incorrect or whether it's just unprovable for the tool. Let me give you a practical example of where this comes up. Let's think about verification of imperative data structures on the heap. These are typically defined using recursive definitions. Now, it turns out that automation for programs annotated with specs that have recursive definitions in them is super hard. It's so hard that it's incomplete even for basic blocks. So even for a block without loops or anything, there is no Turing machine that can enumerate all valid proofs. So there's no really principles for automation in any sense of the word. And because of this, people typically rely on heuristics, which is just like, let's just unroll the recursive definitions and see what happens. The problem with these heuristics is that these heuristics are unpredictable. And they can be unpredictable in the following sense, right? Your VC may actually be valid, your program may be correct, but it's just simply unprovable by the tool. So it'll say, I don't know, and then you can't really fix it because there's nothing to fix. Well, of course, in practice, the engineer is told to give some help in terms of, let's say, adding inductive lemmas, but that brings about a second kind of frustration, which is that these lemmas have less to do with the content of the proof and more to do with convincing the prover that your program is correct. Because remember, it's already correct. So you need to know the internals of the tool, understand that it's using a particular heuristic, and then think, oh, you know what, they must be doing unfolding, surely this is why it got stuck, and this kind of lemma will help it get unstuck. And this makes it not accessible to pretty much anybody but like the 40 or so people in this room, right? So this is the frustration that we attempt to solve in this paper. And so we seek a predictable verification paradigm. And this is what makes a predictable verification paradigm. First, the user is asked for a particular set of annotations up front, right? And these annotations are to be independent of the choice of your tool or heuristic. So you're supposed to give me a set of guidelines. You're not supposed to tell me to depend on, these guidelines cannot depend on the tool that you're going to make me use. And second, once the user gives these clear set of annotations, verifying a program is decidable. And it is this decidability that gives you predictability, right? Because then a tool can clearly just say yes or no. So in this work, we introduce intrinsic definitions, which is a predictable paradigm for verification. It's based on two key ideas, and I'm going to explain them now. So the first key idea is how you write specs, okay? I told you that typically heap data structures are defined using recursive definitions. Let's just throw that out for the second, okay? We introduce a brand new way of doing this. And the way to do this is by doing the following two steps. First, you augment the structure with certain auxiliary unary maps. So in this case, I have a binary search tree. I want to define it. I've augmented it with the parent pointer, with a height value, as well as the min and max of the keys stored under the tree. Then, having done this, you define the structure using certain local constraints, right? And in here, the local constraints are fairly simple as boilerplate, right? Your parent pointer should be the inverse to the left and right pointers. The height is the max of the height of the children plus 1. And you say something about the order of the keys and how the min and max should be computed at a node. You can get this from the children. Now, so this is the kind of pictorial form. Here's how you do it formally, right? So, before that, what makes the definition is that the set of nodes, for it to form a BST, every node has to satisfy the local condition. So that's the idea. So instead of a recursive definition that has a potentially global footprint, you're defining this in some sense much more locally. Here's the formal version of what I said. Ignore the math. Let me tell you what the structure is. So as I told you, the formal way is that there exists some monadic maps, P, H, min, max, such that for every node, some local conditions are satisfied. And the local conditions are exactly what I told you in the previous slide, right? The parent being the inverse rules out DAGs. The well-defined height rules out cycles. So at this point, you already have a tree. And then the constraints on the min and max give you the key order for BSTs. So that's the way that you write the spec. Now, let's look at how you verify things. Let's consider the rotation of a binary search tree. So I have a BST at the beginning, and after rotation, I want to tell you that we have a BST at the end as well. And this is the kind of whole triple, right? So you have the pre-state exists pH min max such that every node satisfies local conditions, and at the end, you want to say the same thing. So because in the pre-state there are these maps, surely there are some values that are there, and I've just invented some values for this example. Now I have to show that these values exist for the right-hand side as well after rotation. Now notice that the subtrees A, B, and C have not changed at all, so I can just inherit those values. That's not a problem. But I can't do this for X, Y, and the root R where it's joined to the rest of the tree. However, we know from the definition what these numbers should be. So for X, I can tell you what the parent pointer needs to be as the inverse of the left and right. I can tell you what the height needs to be by computing the max of its children plus 1. So 4 and 6 plus 1 makes 7. And then the min and max I can do by taking the min of the left subtree and the max of the right subtree, right? So this is how you do it. And similarly, you can do this for Y, you can do this for R as well. So let's go over this a little more slowly. I told you that you can in fact achieve this, but this is like empirical. How do you do this in practice? Let's do this one pointer mutation by one, right? First, you mutate the pointer on X. And when you do this, you break the local conditions on X, right? Because it depended on your child being Y, and you had all these nice maps with all their values satisfying the constraints. You mutated the pointer, now you've broken it. So now we can fix this by asking the user to write some ghost code that tells you how to compute these maps, right? So we know that the parent pointer has to be the inverse. So because the left child of X has become B, the parent of B is now X, right? And similarly, you can write code for the min and the max as well as the height. Now notice here that I'm not really doing this min of left and myself and min of right kind of thing, because I'm using the fact that it's a BST. So my min is just the min of the left subtree. I can just do this. Similarly, then now you mutate Y, that breaks Y, and you can fix Y in the same way. And then you also fix R having done that mutation. And this completes the rotation. Now, you'll notice that for R, I've not really fixed the other things. It turns out you don't need to fix them. The earlier values are already OK. You just need to fix the parent because its child is now different, and I've done so. So these are the annotations that we require the user to write. And this is how the verification proceeds in practice. So, and of course, now I don't have any nodes where the local conditions are broken, right? So wherever it got broke, I fix them. And another way of saying that is that every node satisfies the local condition. And yet another way of saying that is that we have a binary search tree, because remember, that's what the spec says. Every node has to satisfy the constraint. So and to complete the picture, right? So what this does is that it computes the maps that are required for the post state by starting from the maps at the pre-state and having the user write ghost code that updates them. This is a kind of day-to-day, minute-to-minute version of what the verification looks like. There's a lot more nuance to the matter, and the details are in the paper, but I would like to go over them briefly. First, we track the set of broken nodes automatically, right? And then the broken set is like this. If a node belongs to the broken set, then it doesn't satisfy the local conditions. That's kind of the idea. And the broken set is empty at the beginning. You have a kosher structure. And the user must ensure that it's empty at the end by doing all these fixes. Now, we want to keep the user honest in terms of doing these fixes. So we can define for a pointer mutation, which remember, it can break the local conditions on several nodes, an impacted set of objects. We call this the impact set. And we have where the user can declare the impact set, and we can verify this automatically. And for certain data structures, we can even compute the impact set for a mutation automatically. And then when a mutation happens, we grow the broken set with the impacted objects. And when a user fixes the local conditions on a node, let's say Z, you take the Z out of the broken set. So this broken set grows and shrinks throughout the program with pointer mutations and the user's fixes. And at the end, the user has to assert that it's empty. That's the idea. Now, we have a language design that we describe in the paper for how to augment a high-level language with a certain programming discipline that allows the user to do this honestly. It's very cool. I encourage you to check out the paper. But there is one more piece that makes this tick, right? Because remember, I told you at the beginning that you want the VCs, once these annotations are given, to be decidable, because that's what gives you the predictability. And so in the paper, we also describe a way to generate verification conditions that fall into a decidable fragment. This is non-trivial, because remember, things like function calls can have unbounded heap changes, and we have to model them away in some way that's also complete, that's also honest. So I want to give you a little bit of a picture for where our work lies in the space, in the design space of paradigms, right? On the one side, and let's just take the most generous interpretation of what I'm saying. I know all of you will have 100 caveats, but I just want to give you a rough idea of what's happening, right? On the one hand, you have something like lightweight types, as you might find in like compilers, right? Where the the spec is kind of fixed, right? You have a type system that is checking for a particular spec. If you want to check for a different kind of spec, you have to invent another type system. The user burden is low. You just have to annotate your variables and your functions with the types, but the automation is high. You have essentially decidable verification. On the other hand, you have something like theorem provers, where the spec is variable. You can write very expressive specifications, but the user burden is high because you're essentially writing the proof yourself, and the automation is low because you really only have a proof checker. We see our work as lying somewhere in the middle, where the spec is variable, so you can write quite a few things, but perhaps not as much as a theorem prover. And the automation is high. You do, in fact, have decidability. So we borrow one factor from each of the two sides. And the trade-off we have is that the user burden has to be increased more than 0, right? So it's not as simple as types, but you don't have to write the entire proof yourself. It turns out to just be this ghost code, which can be very simple. So that's roughly where we see our work as lying. And I'm sure there are many, many more solutions in this space. But we've really landed the plane, right? In terms of the problem that we set out to see. Previously, we had this kind of picture where you had the yes, no, but you also had this frustrating I don't know. Under IDS, you don't have this because the engine is a decision procedure. Once you give the VCs, all the engine has to say is that yes, your program is correct, or no, one of your VCs is valid. And then the verification engineer goes back and fixes maybe the program, maybe their annotations, whatever was wrong. And crucially, instead of just the program and the annotations like we had previously, we have the user give this extra ghost code. I want to talk briefly about results. So what are we evaluating here, right? We want to evaluate expressiveness and efficiency. Because this is a new paradigm, we have to ask, can you actually express interesting properties? And two, can you verify them efficiently? And the answer to both questions is, to our experience, yes. We verify a suite of manipulation routines on different kinds of heap data structures. And we are able to express full functional specifications for them. And we're also able to verify them fairly efficiently. As you can see, the verification goes through in just a few seconds. And most of the standard structures that you would define using standard recursive definitions can, in fact, be captured using intrinsic definitions. Because you can use something like a height parameter or a rank parameter, you can simulate the least fixed point, and you can get away without having the LFP at all in the first place. And you can just use these local definitions. Of course, we do the verification in Boogie, which is what ensures that we can, in fact, model the VC the right way and generate decidable verification conditions. One very interesting case that we did was an overlay data structure that meshes together a singly linked list and a binary search tree. This kind of structure is used inside a Linux kernel to track the process queues. So the process queues are strung in a linked list, and their PIDs are sorted by a binary search tree. And you want to be able to query for a PID, but also you have this process queue. And because it's a kernel, you have to save space. That's why we mesh these things. We can, in fact, verify them fairly efficiently. And it turns out that it's compositional, right? This is the mind-blowing part. If you had done this using recursive definitions, you would have two competing definitions. You'd have a list, and then you'd have a tree starting from different points in the structure with competing footprints. And if you change anything in the middle, you're dead, right? Whereas here, remember what the spec was. You have to invent some monadic map such that some constraints are true. So we just take the constraints for the list, we take the constraints for the BST, and we just union them. And the verification also proceeds in the same way. When you break something, you fix the list part, and you fix the binary search tree part. And this makes it very compositional and quite simple. I also want to bring to your attention the annotation burden. So you can see here that the annotations, the ghost code with respect to the lines of code is about 1:2, about 2.5, with a few exceptions. This is not atypical for things that require you to write ghost code. There are lots of such paradigms we know. However, in preliminary work, we find that the annotation burden can be lowered by about 60 to 80% with what we call definitional updates. So in the example that I showed you, I told you that height could be computed by taking the max of the height of the children plus 1. We don't need to have the user do this. We can just do it ourselves. And many updates like this are quite simple, and we believe that using program synthesis, we can automate away most of the others as well. And with that, I'm done. In summary, I've introduced to you a new paradigm called predictable verification. It requires you to give the user a description of upfront, a clear set of annotations with clear semantics that do not depend on the tool. And then having done that, it should reduce to decidable reasoning. We have this new predictable paradigm called intrinsic data structures, IDS, that offers predictable verification. It depends on you writing the specs using local conditions that may use some auxiliary monadic maps. And the verification proceeds using a programmatic style that has the user write some extra ghost code, which is this fix what you break methodology. And we call it that because you break some things, then you fix it, right? And it turns out to be surprisingly low cognitive burden. Of course, this is anecdotal from our experience. And in the future, we want to look at several problems. The most interesting of these is to actually develop an IDS-based verification engine for high-level languages like Rust. So we know that doing something like doubly linked lists in Rust can be very hard. And we believe this kind of verification paradigm can help cover those gnarly cases. this kind of what might potentially be marked unsafe if you don't have a good checker. And I also told you about lowering the annotation burden even further by using program synthesis. We really believe that we can write the Ghost code very effectively. The hard part actually turns out to be knowing when to do the fixes. Once you tell me here's what the fixes should be, the fix is actually very simple. When you should fix it in the body of the code, it turns out to be the hard part, and we're actively working on this. Then finally, there is actually applying this to very complex data structures. We are actually very excited because doing the overlay data structure in this simple way got our hearts pumping, and now we want to look at complex data structures and see whether IDS can lower the cognitive burden substantially. And we can also go beyond data structures, right? We can do unbounded message queues, because there are also other unbounded structures that can be defined and verified in this way, and certain things like concurrent data structures. That's very cool. And there are many, many theoretical questions. This is a new logic. We have no idea what the expressive power is, and in particular, we'd like to figure out how they relate to the traditional recursive definitions. Thank you.
Questions? So maybe in the meantime, let me start with one while the rest can think about questions. So I'm just wondering how realistic it is to aim for decidable verification. I mean, very soon you might add nonlinear arithmetic, you might have arrays, and then you need quantifiers. I mean, recursive definitions are just one of the issues that make things tricky, right? But there are many others, and I'm wondering how realistic it is to basically stay in a fragment where you don't have these things.
So, for many of the cases we're considering, we believe that we can get away with decidable reasoning. Even for arrays, you can treat them as symbolic objects. So for example, we were thinking about extending this to concurrent data structures like a Harris list or something like that, right? So when you have an unbounded number of incoming pointers, how we deal with them is to, so I don't have a universal answer for you. But for many cases, we think we can get away with the right kind of modeling. So when you have unboundedly many pointers coming in, for example, like in a concurrent data structure, you can't distinguish between the incoming pointers. So your universal quantifier is essentially symbolic. So the fix for one of them is the fix for all of them. So I think we can do tricks like this and get away. Nonlinear arithmetic is an interesting point. I have not thought about it. Perhaps we can discuss this offline.
Okay, thank you.
So my background is not like in verification very much at all, and this might have touched a little bit on the previous question, but I'm wondering how this would scale up to concurrent data structure or concurrent code and like distributed systems. I know that there was this Iron Fleet project doing distributed systems with Daphne. Is that like a huge challenge, or is that trivial, actually?
So this is, in fact, exactly the question that we're working on right now, and I guess I will tell you the answer next year.
Yeah.
But yeah, so we're looking at refinements and actually trying to make sure that the refinement map holds between the beginning and the end of the code, precisely by using this kind of verification framework.
Cool.
And so refinement maps are much simpler here, mind you, so they can get much simpler. Yeah.
Hi, thank you for the talk. Is decidable actually what you want? Because there's a lot of things like theory of bit vectors is decidable, but not necessarily in a reasonable amount of time. And a lot of the cases where your verification engineer is getting puzzled, the timeout is not because of an intrinsic issue with decidability.
Right. So this is the theoretical framework given enough time and space, right? So
Yeah.
This is at least a set of principles for where you should look at, because the traditional methods, let's say using like recursive definitions or something, don't even meet this criterion. So we're trying to cull out the right space to look at the right paradigms, and in practice, you are going to need to deal with these timeout issues as well. And there we might have even more constraints.
Okay, thank you.
All right, so lunch is